Okay, so let's play a little game. Imagine you're trying to teach a computer what a lamp is, right? Like a regular everyday lamp. You show it tons of pictures, different kinds of lamps, desk lamps, floor lamps, maybe even a lava lamp or two.
Yeah.
But then it comes across a picture of, well, a streetlight or
Yeah.
one of those super modern, like abstract art pieces that's supposed to be a lamp but doesn't really look like one.
Hmm. Yeah.
What kind of challenges do you think pop up when we're trying to get AI to, accurately recognize things in the world around us?
Well, that's a really interesting question, and it leads us perfectly into what we're going to be diving into today. We're going to
Hmm.
be exploring a really cool method for making AI recognition way more dependable.
Okay, I'm intrigued.
The basic idea is this. Instead of just relying on a single AI model, we try to look for agreement and a high level of confidence across multiple AI models, kind of like a team of experts.
Ah, so it's not just one AI making the call. It's more like a jury reaching a verdict. I like it.
Right, exactly. And the material you shared dives deep into a specific approach for making sure that when an AI says that's a table, it's not just, taking a wild guess. It's based on solid evidence and a consensus among its peers.
Gotcha. So we're not just trusting one AI's opinion.
Yeah.
We're looking for confirmation from a bunch of them. Okay, so what's our mission for this deep dive then? What do we want to understand by the end of this?
So our main goal today is to figure out how using multiple AI models and setting specific thresholds for like how much they have to agree and how confident they are actually leads to more accurate and trustworthy results. And then of course we want to understand why this whole thing is so important. Why bother with all this extra effort, right?
Right, right. It seems like a lot of work to make an AI that can tell a cat from a dog. So let's unpack that. What's the starting point for all this? How do we even begin building this super reliable AI?
So it all starts with two key concepts that are the foundation for this whole approach: reproducibility and diversity. Think of them as two sides of the same coin, both absolutely essential for building trust in an AI system.
Okay, I'm familiar with those terms in like a general scientific context, but what do they mean when it comes to AI?
Right, good question. So, reproducibility in AI means making sure that the AI's understanding of something isn't tied to just one specific set of training data. Like if you train an AI to recognize bicycles, you want to make sure it can still do that even when it sees pictures of bikes taken in different places and different lighting from different angles.
So you're saying it shouldn't just be memorizing the specific bikes it saw in the training data, it needs to understand the concept of a bike.
Exactly. It's about the AI learning what a bicycle truly is, not just recognizing a bunch of specific bicycles it's seen before. So to test for reproducibility, you take the same AI model and the same object you want it to recognize, let's say a bicycle, and then you show it different sets of bicycle pictures.
Okay, so different data sets of bicycles. Got it.
Right. And you check if the AI can still accurately identify bicycles across all those different data sets. If it can, that's a good sign. It suggests that it's learned what a bicycle is, not just what the bicycles in one particular data set look like.
That makes a lot of sense. So how do you actually go about testing this reproducibility in a real-world scenario?
Well, the actual testing process is fairly straightforward. You pick your AI model and the object you're interested in, let's say a car. Then you run that same model on one set of car images and then another set, and maybe even a third. If the AI consistently labels the images as car across all these different sets with a high degree of confidence, that's a strong indication of good reproducibility.
Got it. So same AI, same target, different training pictures, consistent results equal good reproducibility. Okay, I think I've got that. So what about diversity? What does that mean in the AI world?
Diversity in this context is all about the AI models themselves. The idea is that we shouldn't just rely on one type of AI model. Different AI models are built in different ways. They learn and interpret visual information differently. So where one model might struggle, another one might excel. It's kind of like getting second opinions from different doctors.
So it's about using a variety of AI brains, if you will.
Right. So instead of showing different pictures to one AI model, you show the same pictures to different AI models. Like you could have a CNN, a transformer, another kind of neural network, and you see if they all agree that the picture shows a bicycle.
So you're basically trying to see if the recognition is solid and not just some weird quirk of one specific type of AI.
Right. And to actually test for this diversity, you follow a similar process to the reproducibility test, but instead of changing the data sets, you change the AI models. You keep the same data set and the same target object and run it through a bunch of different AI models.
Hmm.
If they all come to the same conclusion with a decent level of confidence, that gives you more confidence that the recognition is robust.
That's fascinating. So it sounds like we're building a system where we're not putting all our eggs in one basket.
Mm.
We're diversifying both the data and the AI models themselves.
Exactly. And that leads us to how they actually implemented this in the research you sent. They used three different data sets labeled Model A, B, and C, each with different amounts of data and different numbers of categories.
Interesting. So tell me a little more about these data sets. How are they different?
Sure. So Model A had about 70 examples per category on average and a total of around 2,000 images for 29 different categories. Model B was a bit bigger with 100 examples per category and nearly 3,000 images across the same 29 categories. And then Model C was the largest with 134 examples per category on average and a total of almost 4,000 images again for those same 29 categories.
Okay, so they really varied the amount of data the AIs were trained on. And what about the AI models themselves? What kind of variety were we talking about?
So they used three very different types of AI models. The first one was EfficientNet B1, which is a type of CNN or convolutional neural network. These CNNs are really good at picking out patterns in images like shapes and textures. They work by looking at small local areas of the image and then building up a more complex understanding from there. EfficientNet B1 is known for being pretty fast and lightweight, which makes it good for things like mobile devices, but it might not be the best choice for super complex or abstract images.
So it's kind of like the sprinter of the AI world, fast and efficient, but maybe not the best at long distances. Okay, what about the other two types?
The next one was VIT-B16, which stands for Vision Transformer. This one's totally different from CNNs. Instead of looking at local areas, first it breaks the image down into small patches, like little puzzle pieces, and then it uses something called global attention to figure out how all those pieces fit together. This makes it pretty good at understanding complex scenes, and it can get even better if you give it tons of data. But the downside is it can be a bit of a resource hog. It needs more computing power and more training data.
Ah, so it's the more powerful, but also more demanding type. And what was the third model?
The third model was Swin-based patch for Windows 7 at 224. This one's also a transformer, but it has a hierarchical structure and uses local window attention. So instead of looking at the whole image at once, it starts by focusing on smaller local areas, and then it gradually expands its view. This makes it more efficient and versatile than some of the earlier transformer designs, while still allowing it to understand relationships across different parts of the image. It's kind of like a balance between the other two models.
Okay, so we've got our speedy CNN, our powerful global attention transformer, and our balanced hierarchical transformer. That's a pretty good mix. Now, you mentioned earlier that they used 9 models in total and a threshold of 6 agreements.
Yeah.
Why those specific numbers?
Yeah, that's a great question. They actually started with just 3 models, one of each type, to test the basic concept. But they quickly realized that just 3 models wasn't always enough to get a reliable consensus, especially with trickier or ambiguous pictures.
I see. So 3 models were kind of like a starting point, but they needed more to get a really strong signal.
Exactly. And they actually did a couple of studies to really dig into this, and they found that bumping it up to 9 models significantly reduced both data bias and model bias. It wasn't just about having more models, it was about having a wider range of AI perspectives.
Okay, 9 models make sense. But why did they need 6 of those 9 to agree? Why not just go with a simple majority like 5 out of 9?
Well, setting the bar at 6 agreements makes a system more cautious and less likely to make a mistake. It's like saying we want to be extra sure before we make a call. Plus, the specific threshold of 6 was based on careful analysis and testing. They didn't just pull that number out of a hat.
That makes sense. You don't want the AI jumping to conclusions. So walk me through the evaluation process. Once those 9 models have given us their opinions,
Yeah.
how do we actually decide what to believe?
Okay, so there's a 2-step process. First, we check for agreement among the models, and then if there's enough agreement, we look at how confident they are.
Okay, let's start with the agreement check. What happens there?
In this step, we simply count how many of the 9 models agree on the classification. If at least 6 of them agree, we move on to the confidence check. If fewer than 6 agree, then the sample is marked as unrecognized.
Unrecognized, meaning the AI couldn't figure out what it was looking at.
Right, and importantly, these unrecognized samples aren't just discarded. They're used to further train the AI system so it can learn from its mistakes and hopefully do better next time.
Ah, so it's like giving the AI a chance to go back to school and study up on the things it's not sure about. I like that. Okay, so what happens if we do get at least 6 models agreeing?
Then we move on to the confidence check. This is where we look at how certain those agreeing models are about their classification.
Okay, and I'm guessing there are different levels of confidence that trigger different actions.
You got it. So if the average confidence among the agreeing models is 90% or higher, The system's like, all right, we're good here.
Yeah.
We've got a strong consensus, and those models are super sure of themselves. So it accepts the result and moves on.
So that's the easy case. What about if the confidence is a little lower?
If the average confidence is between 80% and 89%, the system flags it for a human to take a look. It's like saying, hey, we're pretty sure about this, but maybe you want to double check just to be safe.
So it's like a second opinion from a human expert.
hmm
And what about even lower confidence levels?
If the average confidence is between 70% and 79%, they bring in an actual expert to review the classification. And if the confidence is below 70%, even if 6 models agree, it's marked as unrecognized and used for training.
So the lower the confidence, the more human intervention is needed. That makes sense. Now, I know you mentioned some real-world examples in the form of case studies. Can you tell me more about those?
Sure. They had 2 main case studies, A and B. Case study A looked at situations where the images being classified had some kind of problem, either because they were mislabeled in the original data or because they were just really different from what the AI was trained on.
Okay, so case study A was about tricky images that could trip up the AI. What about case study B?
Case study B was even more challenging. It focused on undefined samples, meaning pictures of things the AI had never seen before during its training.
Whoa, okay, so like showing the AI a picture of a platypus when it's only ever seen pictures of cats and dogs. That sounds tough.
It is. And that's exactly why this whole multi-model approach is so important. When you're dealing with completely new things, it's crucial to have both high agreement and high confidence to avoid misclassifications.
Gotcha. So let's dive into some specific examples. You mentioned a lamp example in case study A. What happened there?
Right. So in that example, they showed the AI a picture of a lamp, but it was a very unusual lamp, unlike any the AI had seen before,
Mhm.
and only 5 out of the 9 models recognized it as a lamp.
So it failed the agreement check.
Exactly. And because of that, the system labeled it as undefined to avoid forcing a classification that might be wrong. It's better to say, I don't know, than to make a mistake.
Right, I get it. What about the other examples in case study A?
Well, there was another one with a picture of a valley, but this
Oh,
particular valley also looked a lot like a lake and a river.
so the AI was confused because the image had features from multiple categories.
Exactly. And as a result, the models disagreed, and the image was again labeled as undefined.
Makes sense. So what about case study B? What kind of crazy stuff did they throw at the AI there?
Well, they showed it a picture of a banana, which the AI had never seen before.
Okay, so a totally new fruit. What happened?
Well, the closest match the AI could find was lemon, because bananas and lemons sometimes have a similar shape. 6 models agreed that it was a lemon, but their confidence was only 77%.
Not high enough to pass the confidence check.
Right, so it was marked as undefined and sent for expert review.
Smart move. Better safe than sorry. Were there other examples like that?
Yeah, they also showed it a picture of a vehicle, and this one was interesting because it had features that resembled a train, a boat, a bridge, and even a guitar.
Whoa, that's like a visual Frankenstein.
Right. So the models were all over the place, and no single category got enough votes to pass the agreement check. So it was labeled as undefined.
Okay, I think I'm starting to see the pattern here. Whenever the AI is unsure or dealing with something new, the system steps in and says, hey, we need more information, or we need a human to double-check this.
Precisely. It's all about building a system that's cautious and avoids making claims it can't back up.
So this whole approach seems incredibly valuable. But where could it be applied in the real world?
Oh, the possibilities are huge. Think about medical imaging, where an AI could help doctors diagnose diseases more accurately. Or self-driving cars, where AI needs to be able to instantly recognize pedestrians and other vehicles to avoid accidents.
Yeah, those are high-stakes situations where you really don't want the AI making mistakes.
Exactly. And then there's things like detecting fake news online. An AI could help identify potentially false or misleading information and flag it for human review.
That could be a game changer in the fight against misinformation. But what about the future? As AI gets more and more advanced, what new challenges might we face with this kind of system?
Well, as AI tackles more complex tasks like summarizing documents or generating creative text, we might need to rethink how we measure agreement and confidence. And as AI models become even more sophisticated, we might need to constantly update our systems to keep pace.
It sounds like there's still a lot to explore and figure out, but this multi-model approach seems like a really promising direction.
Absolutely. It's all about building AI systems that are not only powerful, but also trustworthy. That's the key.
And on that note, I think we've covered a lot of ground today. Thanks for diving into this with me.
My pleasure. It was a really interesting conversation.
And to our listeners, thanks for joining us for another deep dive. We'll catch you next time.